Hello, class. So we are on section 10.3, and this is sort of the same thing as section 10.1. It's just in this section, we will be solving bigger systems. Okay, so not two equations, but like three mostly. You could go more, but um, not really. So matrices and systems of linear equations. So the first step is I need to introduce what a matrix is. So a matrix is basically just like a tool that we use. Okay. So here's a system, okay, from like last section. All right, and then you can transform it into a matrix. And what you do is basically this becomes like a bracket, okay? And then you just get rid of all of the letters. So 2, right, there's a 1 here, right? So 1, -1, 4. The equal signs become like this bar, and then 5 and 7. Okay, and this is called an augmented matrix. Okay. And then specifically, we say it has dimensions 2 by 3, which means there's 2 rows, 3 columns. Okay. So the first skill you need to learn is just how to translate between a system and a matrix, which is honestly not that difficult. Okay. Well, it doesn't matter. Minus 2y plus. Okay. So here I have a system, and I'm going to write its corresponding augmented matrix. Okay, 4, -7, 8, 3. Right, there's no x here, right? So that means we're going to put 0, -2, 3, -2. Okay. So we see the bigger the system, the bigger the matrix. Okay. You also should be able to, though, go backwards. So if I have a matrix, okay, you should be able to transform it into a system. And here, technically, it doesn't matter what you call the letters. I'm just going to call them x, y, z anyway. So it's going to be x minus 5, like x minus 5z equals 7, 5x plus 2y equals 10, and then -x plus 3y plus 4z equals 5. Okay, so you should be able to go forwards and backwards. Okay, both, you need to be able to do both. Okay, and so with matrices, basically when the systems get big, we're going to want to use matrices because it's just less writing, right? You don't have to write the letters or the equal signs. But also, as we're going to use the matrices, that means really, from last section, right, I gave you 2 options on how to solve systems: elimination and substitution. Really, when the systems get bigger, we all should be using elimination. Okay, and so elimination works, okay, because we have these elementary row operations, which is what I was doing last time, with like the R2 minus R1. Okay, and so the 3 elementary row operations we're allowed to use is we are allowed to interchange rows. Okay, which basically means we're allowed to swap rows. Okay, so we can swap rows. That's not a big deal. Okay, the second thing we're allowed to do is multiply a row by a non-zero constant. Okay, so you can't multiply a row by 0. That's bad. You're gonna lose info. But you can multiply a row by any number you feel like it, okay? Which normally is going to actually be like a fraction or a number to like do a common denominator kind of situation. Okay, and the last elementary row operation is you can add a multiple of a row to another row. All right, and this is the row 1 plus row 2, or row 2 minus 2 row 1, okay? But these are the 3 elementary row operations, and we use them to solve systems, okay? So let's, solve a system. So here I have a 3 by 3 system. Ten 3x minus y plus 5 is 14. Okay. So step number 1 is translated into a matrix. So 1, -1, 3, 4. 1, 2, -2, 10. 3, -1, 5, 14. All right, now I'm going to show you how to solve a system. But I'll really kind of teach you the idea after I solve this. So here you're just going to see me solve a system. So what I would do is I'm going to do row 2 minus row 1 and row 3 minus 3 row 1. These are going to be the first 2 elementary row operations I pick. Okay. And so that means row 1, okay, is going to stay the same because that's like the one I'm using. Okay. And then now I'm subtracting them. So this is going to be 0, and that's what I want. 2 minus minus 1, that's going to give me 3. -2 minus 3 is going to get me -5. And then 10 minus 4 is going to give me 6. Okay. Now, if you are a little confused by this, you could, right, off to the side be like row 3 is this. And now I'm going to subtract 3 row 1. So I'm going to multiply row 1 by -3. So -3, +3, -9, -12. And then you just add them, right? So 0, 2, -4, 2. And this is what I will put down here. Okay, so 0, 2, -4, 2. All right. So you can always do this off to the side, right? That's scratch work if you don't want to risk doing it in your head. Okay. But now what I'm going to do is I notice like a little bit of cleanup. Okay. I'm going to divide row 3 by 2 because I can, and I won't get fractions. And then just for like a random reason, no particular reason, I'm going to multiply row 2 by -1. I'm just going to switch the signs. Okay. So 1, -1, 3, 4. 0, -3, 5, -6. 0, 1, -2, 1. Okay. Now my next goal is I want to get this to be 0. So what I'm going to do is I'm going to do row 2 plus 3 row 1. Okay, so row 1 stays the same because I haven't done anything to it. Row 3 stays the same because I'm using it. This is going to be 0. All right, this is also going to be 0 because that's the point. All right, and then now I have to, figure out these two. Right, so I'm going to do 5 minus 6. It's going to give me -1. And then -6 plus 3. That's going to give me -3. All right, and now I'm sort of done. I'm going to do row 2 swap row 3. Okay. and I arrive to this matrix. Okay. I'm also gonna just negative it, okay? So really quickly, so like 1, 3. Okay. All right. So why am I kind of done? Okay, because now what I'm gonna do is I'm gonna switch back, okay? I'm gonna switch back into a matrix, I mean a system, okay? And look at what happens. So if I translate this back into a system, I'm gonna get x minus y plus 3z equals 4. I'm gonna get y minus 2z equals 1, and I'm gonna get z equals 3. And we notice, oh, we already have one of them. Okay, and so if you translate back at this step, we can do what's called back substitution. Okay, so back sub. So what this means is I have z is 3. So let me plug that into this one. So I get y minus 6 equals 1. So then y equals 7. And then I can substitute both of these into the top one and get x minus 7 plus 9 equals 4, which is going to be x equals 2, negative 2. Okay? And then you're done. Wait, no, is it negative 2? I'm actually, what? X equals 2, 4, it's positive 2. So, show some work. All right, and then you're done because you got all the letters. Okay, x equals 2, y equals 7, z equals 3. So the answer is 2, 2, 7, 3. Okay, and yes, this is still a point. Technically, what we're doing now is we're doing all of this like in 3D, where these are planes. Okay, not lines anymore. That's all a little too complicated, so you don't have to know that, but just know that this is the answer. Right, x, y, z. 2, 7, 3. Okay. Now, some of you could understand what I was doing, right? Like you probably get like, oh yeah, row 2 times a negative 1, so the signs just flip, right? Or like, oh, I added 3, row 1 to row 2, so this is what happened. Okay. What some of you might be asking though is how did I know to do these, right? Like why did I do these steps? That's what I find most students have like a problem with, okay? Is you could do the steps if you knew them, you just don't know why I'm doing those steps, okay? So I have to introduce what we call row echelon form, all right, which is called REF, and then also reduced row echelon form, which is called RREF. Okay, so these are the two forms that you want your matrix to be in to solve it. Okay, so I'm just going to do examples because the actual definition of row echelon form and reduced row echelon form is like very complicated. You need to do like a leading one, and it's a little complicated, but it's actually really simple if you can see this example. So some of the examples for row echelon form, so REF, okay, is you're gonna want your matrix, okay, and you're gonna want it to look something like this, where x's are just random numbers. You don't care what the x's are. What you care about is that this is a 1, this is a 1, and this is a 0. Okay, that's really the special thing about row echelon form. Okay, and I hope you will notice a pattern here. Okay, so as the matrix gets bigger, this is what row echelon form looks like. Okay, so again, you have these ones, and now you have this zeros down here. Okay, and again, we don't care about any of these numbers. All right, so this is row echelon form for a 3x3. I really would prefer to go back to the color black right now. All right, so we're gonna be stuck with this color for the rest of the class. But and then one more. Okay, so right, this is row echelon form for a 4x4 system. Okay, so again, again, these zeros are down here, ones across the diagonal, and then we don't care about any of these. Okay, so that's row echelon form, and we're gonna want our system to look like row echelon form if we want to solve it the way I just solved it. Okay, because if you look, right, we look here at the end when I decided to go into the back substitution, you'll see that I actually did put it in row echelon form. Right, I got these zeros here and then ones across the diagonal. Okay, so that is really your mission, to decide what row operations you're going to choose. Is your goal will be to get it into row echelon form. Now, okay, reduced row echelon form looks like this. So for a 2x2, it now looks like this. Okay, and a 3x3, it's gonna look like, not that, excuse me, this. And then for a 4x4, it's gonna look like this. And I hope you guys see the difference. Okay, so the difference is that in reduced row echelon form, okay, now you have zeros on the bottom and the top, right? Whereas here, the top didn't matter, right? I just put X's here because it could be like literally any number, right? Like here, right? It was -1, 3, -2. I didn't care what they were. In reduced row echelon form, your goal is you're gonna make these zeros also, okay? And so for the extra work, though, of going to reduced row echelon form, you'll notice that if you translate a reduced row echelon form matrix into a system, right, you're just going to get the answer, right? You're going to get x equals this thing, right? Y equals this thing, and z equals this thing. Okay, so this is like doing kind of like pure elimination from the last section. All right, is that if you go all of the way to reduced row echelon form, you will not have to do back substitution. You will just get the answer as soon as you translate back into a system. All right, but now that we know that, let's do some more examples of solving systems. Okay, so 4x plus 8y minus 4z is 4. 3x plus 8y plus 5z equals -11. -2x plus y plus 12z equals -17. Okay, so we are going to make this a matrix. 4, -11, -17, 4, 3, -2, 8, 8, 1, -4, 5, 12. All right, and then our first goal is we want to get it into row echelon form, right? So the first thing I'm going to do is I'm going to make this 4 a 1, okay? And I'm going to do that by doing row 1 divided by 4, okay? You could do row 1 minus row 2 also, right? You could do lots of things. It doesn't really matter what you do as long as you know what you're doing and it has like a purpose, okay? And then the second thing I'm going to do is multiply row 2 by a -1, okay? So then I'm going to do 1, 2, -2, 1, -3, -8, -5, 11, -2, 1, 12, -17. Okay. Now I'm going to do row 2 plus 3 row 1 and row 3 plus 2 row 1. And I hope you can understand why I'm doing these now. Because right, the goal is to get row echelon form. So the first thing I'm going to do is make these two things 0 under the 1, okay, that I just made. And so you see that by choosing these row operations, I get that. Okay, so 0, 0. And then now I actually have to figure it out though. Okay, so row 2, I'm doing a 3, so 6, so -2, and then -5, and also a 6, so then that's going to be a -8. Wait, what? What? This should be a 1. Excuse me. Thought something looked weird. Okay. All right. Everything's fine though. Okay, so 14. And then down here, I'm doing a 2 instead. So this is going to be a 5 and a 10 and -15. Okay. All right. So that mission accomplished. And now what I'm going to do is divide row 2 by -2. Or no, I'm going to just do 2. Okay. Because that will get me a 1 where I want it. Okay, so 0, -1, -4, 7. And then actually wait, look at the bottom. I could divide the bottom by 5, which is what I'm going to do. So 1, 2, -3. Okay. And then technically my next mission should be to make like this a negative, like right? Like I want a +1. I don't want a -1, but that's an easy fix. Instead, what I'm going to do is I'm going to do row 3 plus row 2, right? Because this cancels really easily. And then I'm going to flip row 2's sign, okay? So on the top, we get this. Row 2, I'm going to flip the sign of. So now it's that. Row 3, I'm adding these together. So 0, 0, -2, and then -3 plus 7. That's going to be 4. All right. And then like technically this is good enough for reduced row echelon form. I know that this isn't a 1, but if we do back substitution right now, like I'll show you. Okay, so if we go back, right, my system looks like this now. X plus 2y minus z equals 1. Y plus 4z equals 7. -2z equals 4. Right, you can solve this easily. Z equals -2. Plug that in there. What do we get? We're gonna get y minus 8 equals 7. So y equals okay, negative. So you're gonna get y equals 1, okay? And then plug that one into here, and this one into here, and you're gonna get x plus 2 minus plus 2 equals 1. So then x equals -3, and ta-da, you're done. Okay, the answer is -3, 1, -2. All right. So, what I'm gonna do now, okay, is I'm actually gonna do this problem again, but like start here. Okay, what do I mean? I'm gonna show you how to go to reduced row echelon form. Okay, so this is if you wanted to do echelon form, right? Regular row echelon form, which is totally fine. You can always do this. All right, I will never force you to do reduced row echelon form if you don't like it. Okay. But I'm just gonna teach you how to at a minimum. Okay, so let's pretend I didn't do this, like any of this. Okay, I'm gonna continue. Okay, so that means I am here. Okay, so let me just grab this thing. Okay. All right, so I'm here. I want to do reduced row echelon form. So that means I definitely do need to divide row 3 by -2. Okay. So 2, -1, 1, 0, 1, 4, -7, 0, 0. This is gonna get me 1, -2. Okay, now my mission is, right, I need these to be 0. Okay, so the first thing I'm gonna do is delete these two, right, the -1 and the 4. And I hope you can kind of see how I'm gonna do that, right? I'm gonna do row 1 plus row 3. And row 2 minus 4 row 3. Okay. So because there's so many zeros, really there's not a lot of thinking that has to happen. These will be the same. Row 3 is never going to change now, okay? But now I subtract 4. So, right, this is 0 because that's the point. And then -7 minus -4 times -2. So that's also known as 8. So then you're going to get 1. All right, and then I'm just adding row 1 and row 3, so that's just going to be a 0. It's going to be -1. All right, and then basically I'm done. Because now I just need to get rid of this 2 as my last step. So row 1 minus 2 row 2. And we will get to the answer. So 1, 0, 0, 0, 1, 0, 0, 0, 1. And you get, right, -1 minus -2 is -3. So ta-da. And then this is your answer, right? -3, 1, -2. And if we look back, yep, that's the answer. Okay. So you can either choose to do back substitution here, or you can do all the way reduced row echelon form and get the point that way. All right. Now, I need to talk about the number of solutions again. Okay. So these problems are kind of long, right? And as you can see, a simple like addition mistake, like if I messed up a symbol, like even like a minus sign, like right here, basically all of this work is worthless, right? Because it'll like avalanche into something very bad and incorrect. Okay, so be very careful when you do these. All right, make sure that you're like double checking. Okay, but just like the last time, we can get exactly one solution. All right, we can also get no solutions. Okay, and we can still get infinitely many. But really, what I want to talk about is the infinitely many case, because now it requires you to do extra work when you get infinitely many. All right, specifically, you're going to need to parameterize a line. Okay, so first, let's just do a no solution. Okay, so you're going to get a system, negative 3x minus 5y plus 36z equals 10, negative x plus 7z equals 5, x plus y minus 10z equals negative 5. Okay, so first of all, I don't know that this has no solution. But you can't just see it, right? What you're gonna do is just what you would do normally. Okay, you're gonna just try and solve it. Okay, so you're gonna make the augmented matrix. One, 10. Okay. I'm actually gonna. What am I gonna do? I'm gonna do row 1 plus 3, row 3, and row 2 plus row 3. Okay, so I'm gonna get 0, 0, 1 actually. And then I'm just gonna swap row 3 and row 1. Okay. So let's see what happens. Okay, so I'm gonna add row 2 and row 3. So this is a 1, it's gonna be a 3, and it's gonna be 0. Okay. And then I'm gonna do 3 times this and add, so it's 0. And then negative 5 plus 3, it's gonna be a 2, negative 2. And then 36, this is gonna be 6. And then negative 5. All right, then I'm gonna do row 1, swap row 3. I'm also gonna divide the new row 3 by 1, or negative 2. Or not. No, I'm just gonna swap row 1 and row 3. So 1, 1, negative 10, negative 5, 0, 1, 3, 0, 0, negative 2, 6, negative 5. Okay. So right, next, if I'm continuing to be normal, right, I want to get rid of this negative 2. Right, because I already have the 1 here, which is nice. So I'm going to do row 3 plus 2 row 2. So the top stays the same. The middle stays the same. But the bottom, right, okay, so I'm going to do it. Right, you're going to get 0. And then you're going to multiply by 2 and add. So I'm going to get 0. And then, excuse me. Did I make a mistake? Yes, I did. This should be negative 3. Right, negative 10 plus 7 is negative 3. Okay. All right, because now when I do 2 times negative 3, I'm going to get negative 6, and this is going to be 0. All right, and then negative 5. And this is the magic. Okay, when you see something like this, you know you have no solution. Okay, why? Because, right, if I translate this back into a system, right, you can just see it right away. Okay, so I shouldn't even be writing this, but that's okay. All right, so 0x plus 0y plus 0z, so 0 equals negative 5. All right, okay, so we see that if we zero out everything and this number here is not also 0, then we're going to get no solution. Okay. All right. Now let's do the infinitely many case. All right. So again, you're not really gonna know it's infinitely many. Okay, you're just gonna see a system and it's just gonna tell you to solve. So we see a extremely similar system. All right. I'm just gonna swap row 3 and row 1 right away while I make my matrix. Okay. So 1, 1, -10, -4, -1, 0, 7, 5, -3, -5, 36, 10. All right, I'm going to do row 2 plus row 1 and row 3 plus 3 row 1. Okay, I'm going to get 1, 1, -10, -4, -1. Oh, just kidding. 0, 0. Okay. 0. Wait, no, just kidding. 1. -3. 1. -2, 6, -2. And then I'm going to divide row 3 by 2. So 1, 1, -10, -4, 0, 1, -3, 1, 0, -1, 3, -1. And then by now you should see the, fishy thing, right? I'm going to add row 2 and row 3. I said that backwards though, but it doesn't matter. Okay, so right, 0, 0, 0, but actually this one also 0. So the whole thing zeroes out, okay? The entire row is 0. All right, this gets you infinitely many solutions, okay? So when only this part is 0 and this is a number, that's no solution. But when the whole thing is 0, that's infinitely many solutions, okay? All right. Now, the problem is, though, we are not done, okay? Because you need to specifically tell me the infinitely many solutions, okay? Because it's a line, okay? So what I mean is what you're gonna do now is, and lots of books do it differently, but I'm gonna say Z, right? Because this is where the Z would be, right? I'm gonna say Z equals T, okay, and box that in. That's my answer, okay? So what is happening here is Z is a variable, right? Okay, what we're doing here by calling it T is actually what we're gonna call a parameter, okay? So we're gonna pretend that T is a number that we actually know, okay? So this means we know what Z is, okay? Which means now we can actually back substitute, okay? So we have X plus Y minus 10Z equals -4. And we have Y minus 3Z equals 1. Well, now I can plug in Y minus 3T equals 1. So that means Y equals 3T plus 1. And I figured out Y. And then I can plug both of these in, okay, and get an answer. X plus 3T plus 1, okay, minus 10T equals -4. You solve this, so X minus 7T plus 1 equals -4. X equals 7T minus 5. And we are done, right? We found z, y, and x, right? And the answer is 7t minus 5, 3t plus 1, t. Okay, don't forget this part. All right. This is the answer, and this is a line in 3D space. Okay, so this is the exact infinitely many solutions that we get. All right. So I would definitely say study this. All right. This is like almost the whole point of chapter 10. But that's gonna be it for today, class. All right. Study the infinitely many solutions case and the just normal, like, know how to do elementary row operations and solve systems. Okay, but that's it. See you next class.